Welcome to today's deep dive. We've got a really fascinating strategic analysis on the desk today, mapping out the high-tech transformation of European inland shipping, specifically in the Rhine-Scheldt Delta. So if you're picturing old-timey seasonal riverboats slowly drifting down the canal, well, you can throw that image right out.
Yeah, throw it completely out.
Because today's inland shipping is honestly a cutting-edge world. We're talking autonomous vessels, crowdsourced river depths, and remote-controlled fleets.
It really is a massive paradigm shift. I mean, inland shipping is this vital artery for international trade, but navigating it now is less about reading the water surface and much more about managing a complex ecosystem of sensors and real-time data.
Okay, let's unpack this digital river concept. The sector is shifting to river information services and these digital maps called inland ECDIS, right?
Exactly. What's fascinating here is how these highly certified systems project a vessel's radar and charts into one seamless display. But the real magic happens when it integrates with AIS.
The automatic identification system.
Right. And that integration allows captains to literally see around corners.
Which is wild. How does that actually work in a twisting river?
Well, AIS uses standard VHF frequencies, that's maritime radio, so the signal easily bounces around physical obstacles. If a massive cargo ship is hidden behind a sharp river bend, it won't show up on a standard radar.
But it will still pop up bright and clear on the captain's ECDIS screen.
Precisely. You see them before you have line of sight.
That sounds foolproof, but there is a catch in the analysis regarding the manual data entry.
A rather terrifying one, honestly. Captains have to manually input their exact ship dimensions down to the decimeter.
Down to the decimeter.
Yes. So if someone makes a tiny typo, say they enter their ship's width incorrectly, it broadcasts that false size. In these extremely narrow waterways, a mistake of a few decimeters can cause really dangerous misrepresentations on the screens of every single ship around them.
Wow. Okay, so here's where it gets really interesting. If one typo can throw off a whole stretch of the river, how do they manage the chaos at massive bottlenecks? I'm thinking about the locks at the port of Antwerp-Bruges.
That port is a hyper-complex environment. Deep sea and inland shipping interact on a millimeter level there. To manage it, they use a system called APCS for reserving lock passages.
It's basically air traffic control for massive cargo ships.
Exactly. Instead of a chaotic race to see who gets to the lock first, ships reserve a slot hours in advance. They can then adjust their cruising speed to arrive exactly on time, saving a massive amount of fuel.
That makes total sense. But the Scheldt River is tidal. Air traffic control is one thing, but airplanes don't have to worry about the runways sinking beneath them.
Which brings us to the W system. WSP calculates dynamic tidal windows to squeeze these huge ships in and out safely. It factors in astronomical tides, but also something called squat.
Squat, like the ship physically sitting differently in the water.
Essentially, yes. It's how a ship sits deeper in the water the faster it moves. WESP calculates all these fluid dynamics to find the absolute maximum safe draft. And because of the WESP system's precision, every single extra centimeter of safe water depth utilized equals roughly 150 tons of extra cargo per ship.
150 tons for one single centimeter? That kind of margin is wild. But to know the clearance, you have to know exactly where the riverbed is. Does the port authority just survey the bottom constantly?
Waiting weeks for official riverbed surveys is too slow now. Enter the COVIDM network. This system brilliantly crowdsources depth data. It aggregates real-time measurements from the hull sensors of hundreds of connected commercial ships, mapping the riverbed dynamically as they drive over it.
So the ships themselves are mapping the river for each other.
It's a brilliant feedback loop, and this efficiency is critical for the sector's environmental survival. Starting in 2026, strict fuel transition mandates will force the industry to adopt alternative fuels, pushing toward hydrogen and electric power to hit a 2050 zero-emission goal.
So every drop of fuel saved by APIX lock reservations or COVIDM mapping counts toward that deadline.
Every single drop.
So what does this all mean for the human crew, with all this automation doing the heavy lifting?
If we connect this to the bigger picture, the Flanders region is now a massive testbed for autonomous ships. We are seeing the rapid rise of shore control centers.
Meaning operators will soon steer multiple ships simultaneously from a shoreside office desk.
Yes, it solves a very real, looming crisis of an aging workforce. By moving the helm to a shore control center, you offer operators regular shifts. That is highly attractive to a younger, tech-savvy generation who might not want to live on the water full-time.
Which means the entire supply chain gets a much-needed lifeline. And that is exactly why you, listening to this, should care. The everyday global goods you buy rely entirely on this invisible, hyper-efficient, and increasingly green logistics web working flawlessly behind the scenes.
It is the backbone of global trade. But it does raise an important question to mull over. If artificial intelligence and office-bound operators completely take over river navigation, what happens to the centuries-old, intuitive river sense of traditional maritime families? Will something vital be lost when the captain no longer physically feels the water beneath the hull?
This raises an important question indeed, a profound thought to leave you with today. Thanks for joining us on this deep dive.